Oh, let's start with the Monty Hall problem. Now, this is just an illustration of how the brain is not able to intrinsically understand probability. So, there's a show called Let's Make a Deal. It's still on TV, I think. And it used to be hosted by this guy named Monty Hall, right? And now I think, is it still Wayne Briggs? Does anybody ever stay home sick and watch it? Okay. Or just stay home. You're in college now. You can have all Tuesday off. But it used to be this. It used to be this. At the end of the show, they take their big winners and they'd say, "You give back all your money, and we'll give you a chance to pick a door." Behind two of these doors are goats, right, or some similar thing, like a pile of dirt with earthworms. And behind the last door is a boat or a pile of money or a car or a vacation, whatever. You guys with me? Something worth a lot of money. So, here's the thing. If you pick a door, somebody pick a door for me. Two. So we got two is picked. And I open door number 1, and I show you behind door number 1, there's a little mutant goat. Right? Oh my gosh. That looks like there's a little spider goat. Right?
Spider goat.
Spider goat.
No? I like that.
No, I like it. Spider goat, then you have spider pig and all that stuff. All right. Okay. Now what? All right, let me bring you back. Let's get past spider goat. So door number 2 is chosen.
No one gets that.
I open door number 1 and show you that there's a goat there, and then I say, do you want to stay or do you want to switch? So the basic question is it better to stay, is it better to switch, or does it not matter?
You should switch.
And some of you guys might have heard of this already, but most people will say it's 50-50, which is completely wrong. It's completely wrong. Why did I open this door? It's more likely I open this door because this door has a prize. Now, I'm not going to open the door with the prize behind it and then go, do you want to switch? And you're like, yeah, maybe the other spider goat's bigger. Let me switch. Do you guys understand? I'm not going to open the prize door. Now, let me break this down a different way. When you chose door number 2, what is the probability that you chose the door with the big prize? 1 out of 3. So what's the chances that the big prize is not behind this door? 2 out of 3 chance. So when I show you the goat is here, what's the chances that the prize is here? 2 out of 3. There's still a 2/3 chance it's not behind this door. I gave you new information when I showed you the goat. That's why it's not 50-50, right? Mythbusters did a whole thing about it. They actually set up a stage and they had people come in. So let me show you. Let me take it to an extreme. And normally people get it when I say this. Let's pretend like this. It doesn't just have 3 doors. It has 1,000 doors. All right, that'll take me a while, right? And you pick door number 2. And I open every other door except for door number 3. And I show you there's a goat behind every other door except this one. Yeah, I'm going to freaking switch, right? Why did I not show you this one? Because it's the prize. You know almost for sure. What's the chances you pick the prize on the first go? 1 out of 1,000. So what's probably the prize in some other door? 999 of 1,000 chance. It's not this one, it's not this. So there's a 999 of 1,000 chance it's this one. So 1 time out of 1,000, you pick the prize, and I can just open any doors I want to and just leave one of them unopened as a goat. But 999 of 1,000 times, you pick a goat, and I just have to make sure I don't open the one with the prize. So yeah, of course you're going to switch, right? So with 3 doors, it's a little bit hard to see. Hopefully with 1,000 freaking doors, you're like, okay, that's suspicious. Why didn't he open that one? I'm going to freaking switch. Is it a guarantee that you'll win? No. But it's a really, really good probability that you're going to win if you switch. So yes, it is better to switch. People hear that though. Here's the other thing about probability. You hear that and then you go, well, that person switched and they lost. You're wrong. Fake news. No. Right? Alternative facts. That lost out to fake news. But probability is never a guarantee, right? You'll feel better if there's a 90% chance the surgery will go well. But does that mean it will definitely go well? No. Right? And that's the other part of probability. You say there's a 2% chance that it's going to snow over here. And you're like, oh, cool, let's just plan everything. And then it snows. You're like, you freaking weather people, what's your problem? They said there was a chance it was going to snow. You can't get mad at them. But we hear 2%, we go, that's zero. That's not going to happen. That's wrong. Of course, unless they're talking about 10% chance of rain in San Diego, then you can basically bet it's not going to rain. It's a pretty everything I've talked about so far is just to show you how the human brain is not designed to understand probability. It isn't. That's why some of that stuff doesn't make immediate sense, and that's why we look at things the wrong way. Okay, that doesn't mean I'm not going to take points off. Yeah. The things we're going to be doing are a little less amorphous than this. Let me make one of my favorite kind of problems, so you know this is going to be on the quiz. And that's to make this thing, it's called a contingency table. Let's just do men and women. So I asked a question of a group of people, and there were some men, some women. Some people said yes, some people said no, some people say maybe. Right? I'm not feeling creative, so you can make your own question up. Maybe keep it to yourself in some case. So I'm going to put in here the totals, like how many men said yes. Let's say that 11 men said yes. Let's say that 2 men said no, and 5 men said maybe. Let's say that 30 women said yes, 5 women said no, and 17 women said maybe. Okay. Just to make up some numbers. So for some reason, this was heavily weighted toward women, but it's just randomly chosen. So what would I put here?
41.
And what would this, so 41, and that represents what? Total number of people that said yes. I love it. So for some reason, people always read, some people read this kind of sideways, but yes, 41 people said yes. So then 7 said no, 22 said maybe. How many men were there? 18. How many women? 52. So how many total people? And I always have some unfortunate soul that puts 140 here because they added these people and these people, but these people are these people, right? So you like added people twice. It's getting freaky. So what did you say, 78? And you can just double check 41, 48, 70, thank God. Let me stop there for a second. Is everybody? So I will give you this kind of problem. I will have something, 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 and then I'll have blank spots on the outside to spur your memory about what the hell to do. Now this is a beautiful problem for probabilities. All different kinds of probabilities. And really, what the hell is a probability? Well, let's see if you guys can tease out what's the probability if I pick one person at random. What's the probability the person I pick is a man? So the biggest mistake I see is somebody says 1 out of 18. What is that person thinking? Well, that's the reality. What they're thinking is, I want one man and there's 18 of them. But if I pick one person, how many people could I pick? 70. Out of those 70, how many are men? 18. So that's the correct way to look at a probability. A probability is always the total number of things that match what you're looking for divided by the total number of things that could happen. So probability, you pick a king out of a deck of cards is not 1 out of 4. Right? It's 4 out of 52. Good old 52 card pickup, right? So I know there's probably a few people in here that don't know their cards too well. I think there are card problems in the book, but they give you the layout of the cards, the suits, and all that kind of stuff. Cards are obviously great for probability questions because you got red and black, and you got 4 different suits, and you got all these different ways to break down a problem. All right, and then let's put this in a few different forms. What is that reduced? 9 over 35. What is that as a decimal? What is it?
I don't know.
Or you
Divided.
you just guessed or what?
Yeah, what's
Okay, now.
I think it's
0.257.
0.257. Close. And then which is, so that's approximately, and that's going to be, what is a percent?
25.7.
25.7. Hopefully everybody knows you move it over twice. I'm not going to do a whole percent lecture. If you don't know the percentages and decimals and all that kind of stuff, review it. Okay. So I want you to realize something. This is the work. Right? On a question like this, there's not much work. This is the work. If you go from here and you give this answer, you haven't shown me any work. And I own a shirt that says show your freaking work, so I think it's important to me. All right? So you must show me this, and after that you can do whatever the hell you want to it. So what about this question? What's the probability I picked somebody who said maybe? Or they said maybe.
22 out of 7.
Yeah. So maybe is 22 out of 70. 11 over 35. Ah.
0.314.
0.314, blah, blah, blah.
Yeah, 31.4%.
Yes, 0.314 what?
14.
2? Okay, as long as that next one, you know, is less than it. Blah, blah, blah. So it's approximately that. So 31.4%. I like it. So, you know, that means a little over 3 out of 10 times. If I do this 10 times, I'd expect to get 3 times somebody that said maybe. Let me say this again. Oh, so here's the misunderstanding. I love to... Did I turn that on?
Yeah,
Yes, thank God. It's always great to have... Oh, I had it pointed at me, but... My little brother asked me a while back, he says, Jeff, are you still teaching probability to these people? I'm like, yes, I am. Jim, what's up with that? He says, what's that shit? That's all crap. It's either going to happen or it ain't. Everything's 50-50. I'm like, James, his real name, I call him James still. He goes by Jim now. I said, James, I'm glad you didn't become a surgeon or a weatherman. Right? What's the chances, Doc? What's the chances I come out as 50-50? So, his way of looking at it is after the fact. Either it happened or it didn't. Probability is before the fact, and that's why it's vague, because there's no way you can ever do math and get the exact answer of what's going to happen. That's where math is not definite. That's probabilities. There's a probability it's going to happen, but... So what does this really mean then? This means that, if I really want to be specific, if I do this 1,000 times, I pick a person 1,000 times, I'd expect on average to get about 314 times somebody who said maybe. So another example, real quick. If I flip a coin, what's probably get a head on the coin? Let's say it's a fair coin. Nobody's messing with it. 50-50, so what's probably get a head? 50%, 1/2. All right. Now, if I flip a coin once, that has no real meaning. I want you to really get this. It's like it's got to land on one or the other, and that's kind of like where my brother goes. And I know this one's 50%, but it's just because it's got 2 sides. You with me? So what the shit does that mean then? It only makes sense over a long time of doing something. So if I flip the coin 1,000 times, number one, I have to rethink my life, but what am I doing? But number two, now it makes sense. About how many heads would I expect to get if I flip a coin 1,000 times? About 500. Now the 1/2 makes sense, and that's what probabilities are. So if your surgery has a 90% chance of survival, that doesn't mean anything for you specifically. Right? If it was done 100 times, I'd expect about 90 of them to be successful. That's really what 90% success means. That sounds worse in a way, but it's the same exact number. Yes?
I have a question about that. Like, isn't it true that if you flip a coin 10 times, and 9 times it's heads, after that it's still a 50% chance?
It's totally. The coin, unless, I don't know, unless something freaky is going on, your coin has no memory. right? Pull little coins and like, oh my God, I remember being in the pocket. No. So of course, if you flip a coin and you get nothing but heads 20 times in a row, there's no greater chance the next one's going to be a tail. No. You're right, exactly. I love it because things don't have memory. Thank God. I like it. And that's something else that goes against the grain. That's why I love it when I see these. Here are the lottery numbers that haven't been picked in a while. Have you ever seen those before? I pay a little more attention to those because I teach probability, not because I play that lottery game. I will every now and again just because. What the shit, why not? But I know it's mostly a tax on the people that don't know probability. But, what was I saying? The lottery.
The coin doesn't have memory?
Coin doesn't have memory. That's true. I don't know why I went to the lottery, but oh well.
Numbers are not being picked.
Oh yeah, the numbers that haven't picked. Same idea. The numbers don't have memory. They don't go, oh, I haven't been picked for a while. It's my turn, right? That doesn't happen. So those kind of things are hilarious to me. But anyway, so that's a little side note about what probability really means. Let me ask you another question based on this. Let me make one a little more interesting. So, yes?
So the law of averages wouldn't apply to the unpicked numbers? Like for example, if like you flip a coin like 5 times and it hits heads, I'd probably bet on tails the next time because of the law of averages?
Nope. That's
No?
completely wrong.
Okay.
Yeah.
So
What the law of averages says is if theoretically there's a 50% chance of something happening, if you do it over the long term, it should become closer and closer to 50% of the time that thing happening. 2 things about that. Number one, it doesn't say a damn thing about a single occurrence.
right.
So just because it hasn't happened for a while doesn't mean it's going to happen with a higher chance on the next time. The other thing about that is it's over the long term. Okay, what's the long term mean? 1,000, a billion, 10 billion to the 10 billionth power, something like that. It's not set. It just says eventually, at some point, it's got to become close to 50%. So if you flip a coin 3,000 times, you get nothing but heads. What should you really think at that point? Something is wrong with that coin. Is it impossible for that to happen? No. So it's not proof that the coin is weighted, but it's pretty damn good evidence that the coin is weighted. So that's where probability comes in. Evidence versus proof. Right? So people misuse probability as proof too often. Yes?
So the screens at roulette tables that show the hot numbers are just fake, pretty much?
Pretty much. They're just trying to get more people over. If there's hot numbers, I'm more likely to go over there. Oh, really? That number? Okay, all right. And they're behind the scenes going, more money. Sweet. All right, maybe. I don't know. I might be busting people's dreams. Hopefully you don't go to the casinos and look for that. Oh, yeah, hot numbers. All right. No. Okay. So, what's the probability? I'm still picking one person, right? Still picking one person. What's the probability I pick somebody who is a man or they said yes? So remember, probabilities are the number of things that match what you're looking for divided by the total. So the bottom is still going to be...
59 and 7.
Yeah, the bottom is still going to be 70.
59?
So how'd you get 59? All right, now let me show you something real quick. So you took all these people, right? And you added them to these people. You see a problem with that? Yeah, you added these people twice. So if there are 30 Democrats in here and there are 22 women in here, does that mean that there are 52 people that would stand up? If I said every Democrat stand up, every woman stand up, will there be 52 people standing up? No, because some of the people that are one would have already stood up the first thing, right? Because there's overlap, and I'm not going to count somebody twice, right? That doesn't seem fair. Everybody should only get counted once. So one thing you could do mathematically, let me see if you guys get this, is you could do 18, that's the men, plus 41, that's the people that said yes. But then I have to subtract 11. 48 out of 70. And then, whatever that is. 24 out of 35. At this point, I don't care about all this other stuff. It's just after the fact. It's business. Whatever you guys want to do, great decimal percent, whatever. The point is the formula. Now that is kind of silly in this instance. What is a better thing to do? Once I count these 18 people, how many yes people have I not counted yet? These 30 people. 30 and 18 is 48. Same number, of course. Mathematically, it doesn't care. Right? But here's the formula right here. This is the formula for OR. Let me show you this. So we're going to make a formula for the probability of A or B, formula for the probability of A and B, and then the formula for something called A given B. The only time the bottom can change from the total is if I give you information. If I said, given that it's a man, what would the bottom be? Given that it's a man. The bottom would be 18, because the bottom is always the total number of people it could be, or things it could be. I like it. I like it. So what is this formula? This is our first official probability formula. Oh my God, I'm so excited. So in the terminology of this problem, 18 over 70 is the probability of a man. 41 over 70 is the probability of yes. And what is 11?
Probability of a man and no.
Beautiful.
Yeah.
Probability of a person as a man and. Somebody said yes, right? Mandy, I like that. A man, and they said yes. Somebody's going to look at that later and go, who's Mandy? So in general, probability of A or B, let me change it to A and B, is probability of A plus probability of B minus the probability of A and B. That's the general formula for OR. Now, I'm going to say this several times. We're going to develop several formulas for probability. If I give you a situation where you can count everything, you really shouldn't have to, and actually shouldn't use one of the formulas we create. Because that's where people make mistakes. If I can count, probability is all about counting. If I can count everything, I don't need some stupid formula, right? I don't. Now, if I don't give you anything to count, if I just say the probability of A is 0.7, the probability of B is 0.42, the probability of A and B is 0.8, you're like, holy shit, I need a formula to plug all that shit into. I got nothing to count. Then that's why the formulas exist. Or maybe. All right. So let's try an AND problem. AND problems are easy when I give you this. Not so easy otherwise. So we're not going to be able to make the formula quite yet. At least we can do one based on this. Let's probably pick somebody who said no and they're a woman. Now here's where people make mistakes. In English, the word and seems to add things. I want you and you and you to go. No, but that's kind of the English version of and. And means like I always call or the nice bouncer and the strict bouncer. Right? Or is the bouncer is like, you can get in the club if you're rich, strike one against Jeff. Or you're dressed nice, strike two against Jeff. Or you know Jim, the bartender. That's Jim, hey Jim, I know Jim, I can come in. So, or, meaning you just have to match one of those things. Or two or three, doesn't matter, at least one. And says you got to be rich, and I'm already walking away. And you got to be dressed nice, and you got to know Jim. I'm like, Jim. Because I can't come in there because that's restrictive. You with me? So I remember back in the day, have you guys ever looked for scholarships? Nowadays you can do it online. Used to be this giant freaking book in the financial aid office. You go in there, everything was free, and you open it, and you read through. Must be a math major. Yes. Must have a GPA. Yes. Must be a woman. Oh crap! Why didn't you put that first? Because that was a bunch of ands, right? It's restrictive. Every new statement was restrictive. So what I'm trying to say, notice how the or number was way bigger. than either one of these alone because it included things from both. The and number will always be smaller because it's restrictive. It says you got to be a man. You got to be you got to say no, and you got to be a woman. So how many people did both of those things? Yeah, there's only 5 people. In fact, another word for and in mathematics is intersection, and you can see why. The intersection of woman and no is 5. 5 people did both. They were a woman, and they said no. Out of 70, because I don't know shit about the person. Still could be any of the 70 people. Was that good?
Yeah, that was good.
Did it make sense? Yeah, I like that. You kind of look down like, we'll find out later. No, I understand. You gotta let some of it sink in. Let's probably pick somebody who said maybe and they're a man.
Same thing.
5 out of 7.
I like it. Just want to make sure. So maybe and man is 5 again. 5 different people, but still 5 out of 7. And then you can reduce it. You can make a decimal. You can do percentage. Normally in a quiz or a test, I'll tell you kind of what form I got to see it in, but you definitely have to start with the ratio of pure numbers, and then you can do whatever you want to with it after that. That's the work. I like it. So if I give you a situation where you can count everything, and is easy. If I don't, and is not easy. We'll have to actually come up with this formula a little bit later. What time we got? Oh, okay. By the way, just so you know, I am going to work the hell out of this problem. I'm sure you already see this happening. But then, like, next time we meet, I'm going to have a little group worksheet that you guys can work on to go over everything we talked about. Okay, so you know, today is my just Bartha lecture on you, and then next time we'll be work on some of the ideas by yourself. I don't know if I ever said the phrase Bartha lecture. So what do you think about this? What's the probability I pick somebody who said yes, given they're a man? So what do we know about the person in this case? We know they're a man. Probability they said yes. I have no idea if they said yes or not. But we're given that they're a man. So like we said earlier, what's going to change? Bottom. Because how many people could it be? 18. We know it's a dude. So it could only be out of those 18 people. So I can basically just do, this. Put a sheet of paper over this on your paper. So this is your universe now, right? So out of those 18 men, how many said yes?
11.
Yeah, 11. I like it. Let's do one more, and then I'm going to try to develop the formula for given. Probability that they're a woman given they said no. Yeah, what's the bottom going to be now? What is it that I know about the person?
7 total. They said no.
No.
To give it no.
Given, no. So that's what I know. Probability it's a woman. So do I know it's a woman? No. The question is, what's the probability that it's a woman? I have no idea. Given they say, I know they said no. So how many people am I talking about?
7.
7. So then you can do like that. Right? Out of those 7, how many women? 5. 0 to 70.72 maybe. What is 5 divided by 7? 0.71. That's my one skill, man. I can't have somebody up me on that. Now watch. Just to make this point for right now, and we'll come back to it later. What's the probability of a woman, period? What's the probability I pick a woman?
30 out of 7.
52 out of 70.
52 out of 70. Now, and that's kind of funny, Jeff. These are pretty close. What's 52 divided by 70?
742.
Only 742? So if I tell you, now the probability of a woman is 74% just about, right? If I tell you the person said no, does the probability of a woman change? A little bit. It goes down a little bit, right? So that's a special kind of relationship. We would say that these two are related in a certain way, right? They are dependent on each other. Depending on whether they said no or not, the probability of a woman changes. So that's going to come up later. Just want to throw that out there right now. See how this is not a big deal. If I know they said no, does the probability that they're a woman, does it change from what it was by itself? Yeah, it did. So that means the probability of a woman depends on if they said no or not. Now people hear that word and they think that means they can't be a woman unless they said no. It depends on no. No. The probability depends on it. It changes a little bit. So for example, if I see somebody get off of a vehicle out in the distance and I can't really see them coming towards me and I can't really make out if they're man or woman yet. They're just way far away, right? Way far away. Don't know. It's just a person. Oh, it's a person. What's probably as a man? 50% roughly, right? If they actually got off a Harley Davidson motorcycle, is it still a 50% chance? Are you sure about that? Now again, I love it that one semester a girl actually got angry at me. She said, I ride a Harley. What are you saying? The chances that the person is a man, if you saw them get off of a Harley Davidson, is higher than 50%. I'm sorry. I'm not saying that no women ride Harleys. I'm not saying that. That's another misunderstanding of probability. Just the probability got higher that it's a dude. That's all. Why? Because fewer women ride Harleys, right? You guys with me? That's another example of dependency. The probability it's a dude depends on the kind of vehicle they just got off of or got out of, right? Okay, maybe. So this idea of dependency, I'm going to kind of bring it up over and over. We're going to develop a test to see if it's dependent or not. We won't do that yet. Okay. So let's see if we can tease out. So let me take this one all the way. Go away. See if we can tease out a formula for given. Let's see. I think I'm done with you. Go away. Well, I'm sort of done. You guys got that written down somewhere. So remind me. So for this one, yes, given, male. Where'd the 18 come from?
The total number of men. Given male.
The number of men, right? And actually, can you guys see? Let me see if you guys can get this. Isn't this equal to 11 over 70 over 18 over 70? Because what would happen to the over 70s? They would just cancel. All right. So I know that 18 is the number of men, but I'm going to put down here the probability of a dude, right? Well, why does that make sense? What always goes in the bottom of a probability? The number of things it could be. And what is it that I know it is? A dude, right? So the bottom should be the given. Now, what was this 11? But the yeses, specifically, they had to also be men. Well, why does that make sense? The only way they could have said yes and shown up here is if they were a dude, because this is the only people that are showing up here right now. Dudes. What does mine say? Sorry. So the top is going to be the number of people that said yes and were men. So visually, I don't know if you guys have ever seen this. Here's the yes box. Here's the male box. Even if you've never seen what's called a Venn diagram, everybody who said yes is in here. Everybody who's a man is in here. And then there are some who did both, right? So if I know that a man happened, that's a really weird phrase, but I know that a man happened. It's a man I'm looking at. What's the only way they could have said yes is if somebody said yes and they're a man. That's the only way they could have said yes. What about this person who said yes? They're out. Because what kind of person is that? Not a man, right? So they're not in consideration in this problem. Okay, right? So let's make sure that this idea holds for this one too. Where'd the 7 come from? Let me start there. Probability of no. And where'd the 5 come from? That was the women and said no. All right, so in general, the formula for a given, probability of A, and let me say this right now, because I'm getting tired already of writing the word given. This is the symbol for given. A given B is the and over the given. That's the way I remember it real quick. It's the and over the given. Jeff. Okay. In this case, the given is B. Again, you saw that formula happen. We actually used it before we even knew it existed. I don't know if you guys see that. So formulas always make things seem a little worse than they really are because they have to be generally true. So there's a billion different situations. In a specific situation, I don't even need the damn formula. I can just see what's going on, right? But again, if I give you values for these, you need a formula so you can plug them in and figure out the one you don't know. Good old algebra is going to come back a little bit. Okay, maybe. Let's see. Where to leave off? Blah, blah, blah. Make sure I don't forget anybody. Oh, that's right. Okay, cool. We got time for that. All right, so one last little thing I want to talk about, and then we'll get out. Oh, wow. Really early. Is that all right?
You're the best.
I had a feeling. Don't get used to it. Holy shit. Yeah, I want somebody to go, I'm paying money for this shit. I had that happen, actually. They didn't say exactly that, but they said close enough. It's like, whoa, get over it. All right. So far we have this. Oops, got it again. Let me see. Let me do something I don't remember to do very often. I just did. What would the formula be for then probability of F given G? Be careful, this is not a division sign, right?
F is G over G.
Yeah, it'd be probability of F and G over G. So I sometimes people don't quite get this idea of this formula is just a template. Any formula is really just a template. And I can put whatever the hell variable I want. Variables are just dummy, they're called dummy variables. They just hold positions.
Are we going to use the union signs and all that crap?
No. Poor little crap. But yeah, I was just saying like or has a symbol like that.
Yeah.
And has a symbol like this. Yeah, I don't think the
You're
book.
not really
No, the book just says and or. I'm not concerned. But see, like or, it's like you or you. I don't care. See, you, you, yeah. And I don't know. And it looks like an A without the little thing in the middle, right?
Are we allowed to use it before you?
Oh yeah, totally.
Okay.
Man, I'll get a little tear if you use some math symbols correctly. Oh. Real quick, what would probably a B given A be?
That's the one.
Yeah.
Probably A and B. How's it related to probably B and A? What do you think? Probability of no and man versus probably man and no. Are they different? No. Of course they're not different. So I should have kept my little. So if I have 4, 2, 1, 7, A, B, C. What's probability? C and A. 4 out of 14. 14 total, right? What's probably of A and C? So, okay, so they're the same. Of course they're the same, right? What's the chances that you and you went to the store? No, I mean you and you went to... It's the same freaking people. What the hell? So yes, we do incorporate that idea with and. It doesn't matter the order. So these are actually the same. Right? Okay. So that was one little thing while I was thinking about it. I wanted to shoot at you. Oh yeah. Let's talk about the idea of mutually exclusive, and then we'll head out. Mutually exclusive. Some books call it disjoint. But, yeah, I like that. This joint, that joint, I don't know which joint. Mutually exclusive. I like this better because the name tells you what it is. So, guys, what's exclusive mean? So if it was like private, it only lets certain people in, or certain groups, or certain whatever. So if you have an exclusive party, well then not everybody can go, right? Mutually means both sides, right? Both things. So if it's sort of like that old thing about, well, if you won't let me in, then I don't want to be in there. So we mutually exclude each other. Right? I don't want you in my house, and you don't want me in your house. That's fine. So we mutually exclude each other. So mutually exclusive means neither one has any elements of the other one. So I used to use cats and dogs, and this is old now, but there used to be a cartoon, cat dog. Yeah. Okay. I actually never got into that cartoon, but anyway.
No.
The biology of it just bothered me to no end. And now I just use rock and salamander, right? Are there any rocks that are also salamanders? No. If it's a rock, it cannot also be a salamander. Are you with me? Do you know what salamanders are? Are you with me? It's not a character from Harry Potter, right? Professor Salamander. They're amphibious creatures. Salamanders. They're sort of like newts. You like newt better? No? All right. So mutually exclusive means, if I want to get really technical, if A and B are mutually exclusive, then the probability of A and B is 0. You with me? I mean, that's really what it means. They just don't share things. So give me an example of something that's not mutually exclusive. I did that earlier. Democrats and women. Are there women who are also Democrats? Yes. So that's not mutually exclusive. So that's how you attack. That's how you attack a problem. To say, are these mutually exclusive? You just stop and think, could one of these also be this? Okay. So what about, somebody who's under 30, somebody who's a billionaire? Is that how you spell billionaire? I don't know. I'm nowhere near a billionaire. There it is, maybe. Thank you. Are those mutually exclusive? I don't know. How old is that one dude that made Facebook and all? He's probably over 30 by now. He's still, well, when he was 20, so he's...
But he was 20.
Yeah, he was a freaking whatever, right? So this is not mutually exclusive. So not mutually exclusive, right? So how about somebody give me something that is mutually exclusive? Say again?
Pens and pencils.
Uh-oh.
What?
I think I saw pens and pencils, right? So I think I've seen something that one end was a pen and one end was a pencil. To be honest, yes. It sounds all like the cartoon, but I won't. I love it, right? I don't think they've invented yet the orange juice that you can just pour on your toothbrush. Not yet.
Apples and oranges.
Apples and oranges. I don't know. Somebody working on a hybrid apple orange. I don't know. It'd be an appenge. An oral appenge.
Tennis season football.
All right. Do you guys start to see how to look at this? So they give you a problem, they're going to give you some situations, and you got to figure out, could this person also be this? Or could this thing also be this type of thing? If so, they're not mutually exclusive. If it's impossible, they are mutually exclusive. if one cannot also be the other. Right? Like dogs and ferns. Right? Those are mutually exclusive because if I have a fern in my hands, I don't also have a dog. It's not a dog at the same time, right? It can't be. But dog and mammal, that's not mutually exclusive because every dog is a mammal. Yes?
So if we come across a problem on the homework that's mutually exclusive, we just write that as the answer? Or
Yeah, the question is going to be, are these mutually exclusive or not? And you could just write M dot E. I like it. I like it. All right, that's remarkably early, and I don't mind. That's fine with me. You guys can go start working on corrections on that test or whatever else